then just make conclusion based on p-value. Alright, so lecture 5. So this is one of the problems that we may that possible, the problem that we can have when we construct an econometric model. So there are a number of different possible problems, including multi-collinearity, autocorrelation, as well as heteroscedasticity. Okay. So we need to make sure. So in order to use ordinary square estimation approach, we need to make sure that the model that we estimate satisfies all the assumptions, okay, including what we call that the absence of linear dependency between independent variables. So you recall that one of the notes given earlier, okay, it discussed about linear dependency between independent variables. So when there is linear dependency between independent variables, between x, then we have the problems of multi-collinearity or collinearity between independent variables or between the explanatory variables. So what is multi-collinearity? Multi-collinearity is a problem when explanatory variables are highly correlated with each other, so it is often hard to determine their individual regression coefficient. So we have linear dependent or linear relationship between x, okay, between the regressors independent variable. So we have two types of collinearity. So perfect multi-collinearity and imperfect multi-collinearity. So perfect collinearity, it refers to a situation where when we have exact linear relationship between two or more x, okay, two or more explanatory variables. So remember before the assumption, in lecture 2 we discussed about this one. So meaning that there is no linear relationship between independent variables. And then you refer to the lecture 1 also discussed about that. They also introduced or talk about that in this note. So about linear dependency, linear dependence. So meaning that in our X matrix we should not have, recall that in our X matrix we should not have any of the columns of the X matrix to have linear dependence with the other columns. Okay, your X matrix, remember this one? I think that's also, for the case of this one the X matrix. So we can express our variables in matrix form. So we have X matrix. So X matrix here, meaning that it requires one of the requirement or assumption. All columns in this X matrix do not have any linear relationship between between any of them. Okay. So if there is, let's say, a linear relationship or linear dependency between different columns, then we have the problems of collinearity, multi-collinearity. So we have again two types of collinearity: exact linear relationship between. We have as if perfect multiplicity, we have exact, meaning that one column of the X matrix exactly equal to the multiplication of other column. Let's say just now we have this one. So let's say we have the second column, x1, the first independent variable, is exactly equal to 2 times of the second variable, independent variable, or the third column. That's what we call as exact or perfect connectivity or exact relationship between different independent variable with different x. So imperfect multicollinearity, when we have two or more explanatory variables are approximately linear related. So meaning that, for example, let's say the first regressor equal approximately, not exactly the same, okay, but it is approximately equal to the 2 times of the second regressor. So that's the difference between perfect and imperfect collinearity. Okay, so perfect exact relationship equal, so this one equal to what we call that linear convention of other variables. So if imperfect, approximately equal, almost the same value but not exactly the same. Okay. So this example, for the case of perfect multicollinearity, when functional relationship exists among independent variables, so that is given, that is the sum of the combination or linear combination of linear independent variables equal to 0. For example, this one. So let's say x1, just like I mentioned just now. So x1 equal to negative 2 times x2. So exactly equal. So this one equal to negative 2 times of x2. So we have perfect collinearity between x1 and x2. So if multicollinearity is perfect, then the regression coefficient of the x variables, the coefficient for the regression coefficient is this one, the regression coefficient, beta 1, beta 2 cannot be are indeterminate, so we cannot identify the value, and the standard error SE are infinite. Okay, so that's the implication. Imperfect multicollinearity, when functional relationship exists among independent variables, as given by this, so meaning that it's not equal to 0 but equal to an error term. So meaning that whether positive or negative. Okay, this one. Where V is stochastic error term. So as an example, similar to this one, but this one perfect is equal to 0, but this one equal to certain value, whether negative or negative, negative, positive, but it's also possible 0. It's also possible that certain value, some of them equal to 0, but some of them, the combination of x1, other value of x1 and x2 equal to either negative, positive, but they are almost similar values, so almost approximately equal. So then the regression coefficient poses for this case, for this situation, if we have imperfect collinearity, the regression coefficient poses loss and error, which means the coefficient can be estimated but with less accuracy. So we can estimate, but the estimate is not accurate, so it's not that reliable. It's not reliable. So we produce an unreliable estimate of standard error. So which assumption of the classical linear regression model is violated? So Norilly square, whereas Norilly square assume that no independent variable should be a linear function to other independent variable. Recall that each estimation postulate of the Norilly square regression provide an average value of changes in y for each unit of changes in x holding other independent variable constant. So normally that's how we interpret the estimated coefficient. So we say that when we estimate, so we get beta hat, beta 1 hat, beta 2 hat. So we see that when x1 increase by 1 unit, then y will increase by beta 1 hat, the estimated value, by holding other x to be the same value or remain the same unchanged. So but if there is a relationship between x and this x and other x, when this x change the value or increase 1 unit, then other x also will increase the value as well. So that's the problem. So this one, if one of the independent variable is a linear function, so ada independent variable, hence when its value changes, the value of other independent variable also changes. Okay, the related variable. As the result, on the radius square, whereas cannot estimate the coefficient of the slope coefficient, beta 1, beta 2, and so on. And although perfect multicollinearity may exist in theory, it seldom occurs in real world. Example of perfect multicollinearity is when the researcher has assigned the same variable twice in the model. So let's say you mistakenly, when you estimate, for example, in views, you mistakenly type the same variable. So let's say you have x1, y space c space x1, and then space x1 again, the same variable you include twice. Okay, or you have the same in X matrix, you have the same values, the same value of variable for this one, the first X, and then the second X also the same variable, the same values and the same values. So you have this one exactly the same. Then you have perfect collinearity lah. You have the perfect multi-collinearity. And another example is in the case of dummy variable when all dummy variable included this known as dummy variable trap. Okay, so we haven't discussed. I think in week 8, we started all 9. Week 8. After midterm break. I think after midterm break. After midterm test. Week 11, week 10. I'm mistaken. We discussed dummy variable, the use of dummy variable to represent the effects of different categories. So dummy variable is just a value 1 or 0. So let's say you have a variable representing the income of different individuals, male and female. So let's say you have 100 individuals, some of them male, some of them female. So you want to measure how the salary or income differ by gender. Then you can create a variable, the one that we call a dummy variable, to represent different gender, male and female. So we can have so male and female, we have two categories. So we can create dummy variable for male, and then we also can create dummy variable for female. So dummy variable just value 1 or 0. So let's say you create dummy variable for male, and then meaning that the value is supposed to be 1 if that person or that observation belong to male. Then you put 1. Okay, so meaning that here your values, let's say this is the income or salary. Okay, and then you create dummy variable. You have intercept here, beta 0 intercept. How you understand now why we have 1 for the first column? We have 1 the first column in the X matrix because we have the intercept beta 0. Okay. So let's say the first x1 is dummy variable for male. So let's say you create a variable to represent whether this observation belongs to male or not. If it belongs to male, then you put 1. If not, you put 0. That's dummy variable. Okay, that's what we call the dummy variable. If it is equal to 1, if the situation exists or condition exists, if not 0. And then we also can create dummy variable for female at the same time. We also create dummy variable for female. So let's say if the first observation belongs to male, then this one supposed to be 0 lah. Okay, and then if let's say second person has is female, then the first dummy variable is supposed to be equal to 0, and then this one 1 lah, because this one dummy variable for male, this one dummy variable for female. Okay, the x1 for male and x2 for female. So what happens when you include dummy variable for all categories? What happens? The sum of the values for all dummy variable will be equal to the first column equal to 1. So this one, so either let's say these two columns x1, x2, these two columns x1 and x2, both are dummy variable. First for male, second for female. So either one can be equal to 1, the another one must be 0 lah, right? Because this person cannot belong to both categories. It must be either male or female. It cannot be both. Okay, so let's say the first person can only be male or female. So either this equal to 1. And then the second person also the same. So the sum of dummy variable, if you include dummy variable for both categories, so what you have, the sum of this and this equal to 1. All equal to 1. You can imagine lah. Understand lah? Can I imagine? And say you have a model. So just okay now. So your Y, let's say income or salary, monthly salary. So you want to measure, or you want to construct a model that allows us to see the difference between salary for male and female. So we create dummy variable. Dummy variable just value 1 or 0. So your x1 dummy variable for male. So meaning that the value of male. So let's say this one is x1 is for male. So it is equal to 1 if the observation belong to male. Okay. And 0 if not. So we can create another variable for female, dummy variable. So let's say x2. If let's say the first observation belong to male, this one equal to 1, this one must be equal to 0. Cannot be 1 for both. Then that's a weird person. You have both genders. Okay, so this one, let's say the second observation, y2 this salary, this one salary, monthly salary. Y1, Y2 for second observation, second person. Let's say this one is person, second one is female. So we have 0 and 1 lah. Right. Dummy variable can only take two values, 0 or 1. So let's say the third one is female again. So you have same 1. The next one male. So you have x1, 1, x2, 0. So this plus this, what happens? If male plus female, the dummy variable, x1 plus x2. So you have 1, 1. Right. So this is equivalent to the first column. Okay, remember we cannot have any linear dependency within this column, this matrix X. So that if let's say you create dummy variable, and then you include dummy variable for all categories, and then the sum of all dummy variable will be equal to 1, which is equal to the first column. Okay, the first column for beta 0. Remember, the first column all equal to 1. We have all equal to 1. Why? Because we have beta 0 and intercept number. Intercept. So that when you multiply beta 0, you get beta 1. So that's what we call a dummy variable trap. Dummy variable trap is a situation when we include dummy variable for all categories. So let's say you have 4 categories. Let's say you have season. Let's say you have, let's say you have education level, educational background. So let's say you have 3 categories: primary school, secondary school, tertiary. So you have 3 groups. You have 3 categories, and then you can create 3. You can do the same lah. So you can create a variable for 3 categories. For primary school, those who have on up to primary school, secondary school, tertiary, university. So the same lah. So each of the person can only have 1. Can only be equal to 1 for any of the category. The highest educational level highest. So see the same lah. So you take sum of them, 3 categories, 3 dummy variable. You take sum of them equal to all equal to 1 at least, which is equal to the first column. So normally, so later we will discuss in detail lah. When we discuss about dummy variable, when we have when we want to include, if we want to include dummy variable for different categories, we should not include dummy variable for all categories, we should exclude one. Okay, let's say for male and female, you just need to include one lah, either male or female. You cannot include both. If you have normal intercept, okay, so the normal practice is that we have the intercept, but we only exclude one of the category. Dummy variable, we exclude one of the category. Okay. We can have all categories, but we cannot have this one. If let's say you decide to include both male and female dummy variable, so what you need to do, you have to make sure that there is no any other column equal to the sum of them. So how to do that? You have to exclude the normal intercept with the zero. If let's say you don't have intercept, then okay lah, because you don't have a column for everyone. But the normal practice is that we have the intercept, and then you have to exclude one of the category dummy variable. You do not include dummy variable for all categories. Otherwise, you have sum of the dummy equal to one, all equal to one. Okay. So now the normal practice is that if let's say you have two categories, you just include two. Let's say just now you have the highest education level. So you have primary, secondary, tertiary. So you just put two lah, so primary and secondary. So let's say you have three categories. So you just include two. So let's say the first person is has the highest admission level is primary, and then one, this one zero lah, this one secondary school. Okay, and then let's say the second one it has secondary school, and then let's say the third one has tertiary. So both zero lah. Okay, both zero because you exclude the tertiary one. Okay, meaning that when you take some of them, not all equal to one, some of them equal to zero. So you don't have the problem. You don't have linear dependency between this and the first column. Okay, so that's the normal practice. We do not include dummy variable for all categories. We take out one. Okay, that one we discuss more detail in the lecture 10. I'm mistaken. We've got dummy variable. So that's what we call as dummy variable trap. When all dummies is included, okay, I mean all categories. So this one dummy variable for all categories. Okay, so let's say you have two categories, you include dummy variable for both categories. You have three, you put all the three. And then you have what we call as dummy variable trap. So it's possible to have perfect cardinality. You have this kind of situation. So if you have exactly the same values appear in different variables, and then you have exact values, and then you have what we call dummy variable trap. Okay, and it is common to find imperfect multicollinearity in economics modeling, as some of economic variables move in the same direction or systematic manner. Example, an increase in the interest rate by central bank will trigger changes in the bond value. All these variables are in the stock market as well. So meaning that when the variables that we have in the model, they are moving to the same direction, then we can have what we call as imperfect cardinality between the regressors, between independent variables. So there are a number of effects of multicollinearity. Whenever we have perfect multicollinearity, then we are not able to get estimate of the release square. So later we do an example lah. So when we include, let's say you mistakenly include the same variable in the model, then you will not get. Or maybe we can take example lah. So this one, the example that we are going to use for this lecture. This one we have. So this one just show example, you don't need to do. So let's say now we have a model, we want to construct model to estimate assumption, and then we have two regresses, independent variables, income and wealth. So let's say you mistakenly include income twice, then you have perfect causality, and then you will not get, you be able to get estimate lah. For example, if you type, not need to do, I just want to show example, it's just an example. Let's say you mistakenly include the variable twice, your x1 and x2 is the same variable, and then the third one. So it says that near singular metric. Okay, so maybe perfect, basically is perfect causality because you mistakenly include the same variable twice in the model. So you have x1 equal to x2 lah. It's like x1 equal to exactly equal to x2. So why we cannot get the estimate? Because you recall that the way that we calculate you remember the formula that we used to estimate to get the estimation, this one. So when there is perfect causality, then the inverse of the x transpose x not exists. Okay, so we are not able to get the calculation cannot be done. Okay, the inverse of x transpose x not exists when there is perfect causality between independent variables or between different columns in the x matrix, in the x matrix. Bigger value of the errors resulted in wider confidence interval, hence the t-statistic becomes smaller. So recall that the formula that we use to calculate t-statistic is just the estimated value of coefficient minus hypothesis value divided by standard error. Remember that one? Where do we have that one? Okay, recall this one. The formula that we use to calculate statistic, the estimate of the coefficient minus hypothesis value divided by standard error. Okay, the standard error. So the present of multi-causality will make the standard error to be larger . Okay, it will make the standard to be larger. The present of multi-causality imperfect lah. Perfect we will not be able to estimate. Imperfect causality, when there is imperfect causality, then the standard error here, this one, is going to be larger as compared to when there is no multi-causality. So when it's larger, then our t is going to be smaller. Okay, so when something divided by something bigger, then the whole thing, the t-statistic is going to be smaller. Okay, smaller when t-statistic is going to be smaller, then there is tendency that there is the tendency for us to do not reject analysis. So t, you imagine t distribution, so t becomes smaller. So meaning that it has more tendency to for us to do not reject the null hypothesis, because t smaller than critical value, we do not reject. Imagine the t distribution. Okay, so when t smaller, then so less likely to reject the null hypothesis because it is smaller than critical value. Okay. So that's one of the implications. So meaning that although in reality it's supposed to be significant, but because of the multi-causality, it makes our estimate to be insignificant. So that we make conclusion, the conclusion that we make based on the hypothesis testing is incorrect or not reliable. Okay, because of the multicollinearity, we conclude that the X has no significant impact on Y, but that happened because of the multicollinearity problem. Okay, the impacts of multicollinearity. And then the estimator is sensitive to any changes plus or minus a few sample size, mid to sample size or insignificant variables. So when we have this problem, so normally if you change the sample size, you add more observation, then it will have significant change to the value of estimate for the certain parameters. And then number 4, estimate have wrong sign. So although we expect to be positive, but after we estimate we get negative. Later we see an example. So we have an example. You see that because of the collinearity, multicollinearity, then we get estimate of the parameter with different or incorrect sign. It's supposed to be positive, but we get negative because of the collinearity, multicollinearity. Alright, so to check for multicollinearity, there is no specific test is available for checking multicollinearity. This is because in any regression with more than one independent variable, will have a small degree of multicollinearity. Hence, the checking is based on how big or how serious the problem exists. Okay, so if the problem is so serious, which make the estimate to be incorrect or to be not reliable, then we have to do something. Otherwise, we can just ignore the problem. So how to detect? So there are a number of ways that we can use to what we call that to identify if there is the problems of collinearity, how serious. If there is serious problem of multicollinearity, so we have a number of different ways that we can use. The first one by checking the correlation between independent variables. So let's say you have 3x in the model, then you just check the cross correlation between x1 and x2, correlation between x1 and x3, between x2 and x3. Okay, that's why we got pairwise correlation between explanatory variables. So one method to check for probability is to look at the correlation coefficient between the two independent variables. As we know, the correlation lies between -1 and +1. So the nearer the value of correlation coefficient to -1 or +1, the bigger is the existence of serious multicollinearity between independent variables. So this is useful to see the possibility of having collinearity between two independent variables. But it's not really useful if the linear dependence happens between more than two variables. So let's say for example this one lah. So x1 plus x2 equal to x3. If x1 equal to x2, then we should be able to see that the possibility of having collinearity between x1 and x2 by looking at the correlation between x1 and x2. But if the linear dependency happen or exists in between three or more than two variables, then meaning that the use of correlation not really suitable or not really useful, to give us a warning that there is a possibility of collinearity between variables or independent variables. And then the second one, if you inspect the result of estimation and you see that the large overall F statistic for testing usefulness of predictors but small or insignificant T statistic. So you inspect the F statistic that represent the overall significance of the variable of the slope parameters. So I say that I explained to you before, you recall that the F test statistic we use to perform joint F testing for all slope parameters in the model. Okay, beta 1, beta 2, beta 3. And now this is all equal to 0, alternatively at least 1 not equal to 0. So normally when we have multicollinearity, then we have contradictory between F test and T test. So for example, it's possible that F test suggests that at least one X to have significant effects on Y, independent variable, but when you perform the individual testing, then you see all are insignificant. So that one of the indication that the model suffer multi-equality problem. Yeah. And then another way to check is by looking at the VIF, the variance inflation factors. If the value of the VIF, variance inflation factor, large, then it indicates for the present of serious multi-equality problem. Okay. So variance inflation factors (VIF) is used to measure multi-equality by regressing one independent variable to the other independent variable. Subsequently, for each regression, calculate the VIF with the formula VIF equal to 1 over 1 minus the coefficient of determination, so R square, 1 minus R square, 1 over 1 minus R square will give us what we call as VIF, variance inflation factor. Take note that the R square used in the above formula comes from the auxiliary regression, means that we regress each of x against other x. So let's say you have 3x, and then you regress x1 against x1, x1 against x2 and x3, and then you do again, you repeat, you regress x2 against x1 and x3, and then you repeat again, you regress x3 against x1 and x2. So generally, researchers believe that VIF, the value of VIF greater than 10, show the existence of serious multi-equality. So this one depends. I mean, certain book says more than 5, but some books says more than 10. That can give us what we call that just the value that when there is a possibility, high possibility that there is a serious multi-equality problem exists or appear or present in the model. So the variance inflation factors can be thought of as a ratio of the estimated variance of the estimator, okay, the beta, to what the variance would be with no correlation between independent variable in the equation. So R square of 1, if let's say you regress any of x against other x, any of the regressor or independent variable against other independent variables, so you get it equal to 1, then indicates perfect multi-equality, produce VIF equal to infinity. So let's say you regress x1 against other x, so you get R square equal to 1, so 1 minus 1, 0, okay, 1 minus 1, 0, so it is so perfect quadratic, VIF equal to infinity. Okay, this one. And take note that the R square used in the above formula come from the, okay, the one just now, that each of x regress against other x. So R square of 0 indicating no multiplicity at all produce VIF equal to 1. So if you regress x and each of x against other x, it produces R square equal to 0, then the VIF equal to 1. So there is no problem of multi-equality problem at all, because the value is equal to 1, because it's 1 minus 0. So the variance inflation factors measure how much the variances of the estimated regression coefficient are inflated as compared to when predicted variables are not linearly related. So it give kind of what we call an indication, or just estimate how much how much the value of the variance of the estimator increase or inflate as compared to if there is no multi-equality problem. So this is an example, the same example data that we used just now, the one that I used just now. So we have consumption, income and wealth. Let's say we want to construct a model to explain consumption using income and wealth. Okay, income and wealth. Data of monthly consumption, monthly income (INC) and wealth WLTH. So you can inspect the correlation between two. So basically, the first step, you inspect the cross correlation between independent variables that can give you an idea whether there is high possibility to have serious problems of multi-equality or not in the model. So let's say we have data here. So we have this data. So you open as one the example. So here our dependent variable consumption, we have two independent variables, income and wealth. So a good practice is that before you estimate, you inspect the cross correlation between your independent variable in order to see again the correlation, because correlation can give an idea about the possibility of having serious multi-connected problem in the model. So you can go to, let's say you go to quick group statistic correlation. So I hope you already know the concept of correlation. What is correlation? Correlation represents association between two variables. Okay, remember the scatter plot. Scatter plot when x increase, y increase, that one correlation positive lah. So when x increase, y decrease, that in that case the correlation negative. Okay. So correlation, you can just type the list of independent variables we have. So income and wealth, WLDH. Okay, then okay lah. So you get correlation. This is what's called as cross correlation. Cross correlation table. So correlation between income and wealth is given here, 0.998.962. So quite high lah. So almost 1. Remember correlation take values between -1 to +1. So it is close to +1. Okay, so again, so meaning that we have to be careful lah. So when you regress, you estimate regression model or correction model, you have to be careful for the possible present of serious problems of multicollinearity, because there is high correlation between the two independent variables. Okay. So and then we regress and see, you regress, you will see that, okay, so another thing that you should do when, before you estimate model, you should state, or you should identify the prior expectation, the sign of the prior expectation of about the sign of the estimate. So let's say, income and consumption, what is your expected relationship between consumption and income? When income increase, consumption is supposed to be increase or decrease? Increase. When income increase, we expect consumption for that. Consumption also increase, so we expect the estimate to produce positive, to have positive estimate of the slope. And then wealth and consumption, what we call that a richer person supposed to consume more, positive as well. Okay, so we expect wealth also to have positive effect on the consumption. So both positive, income positive, wealth also positive. So we have now, before we estimate, we already have that in our mind, whether it's supposed to be positive or negative. If you're not sure, you can check the theory, for example, refer to the theory, or you can check the previous study in order to see what is the supposed to be what we call that relationship between dependent variable and independent variables. So after we estimate, you can see that income positive, okay lah, but wealth has negative estimate. So meaning that wealth have a wrong sign. It's not as what we expect. Okay, it is negative, although we expect to be positive. Okay, so overall test shows that model is significant. Okay, you estimate model. So this one, we estimate model. You go to quick equation. Quick estimate equation. Okay, so you type the variable that we have. So we have assumption and C for intercept. Remember C for beta 0 intercept. And then we have income, INC, and then well, we LTH. Okay, so we get this estimate. So this is estimate for the beta 0, estimate for beta 1, estimate for beta 2. So just now, as I mentioned, as stated in the note, for income it is okay, but it is not significant. See the p-value greater than 0.05. So we do not reject. So we say that there is no significant effect of income on assumption, right? Because p-value greater than 0.05. For wealth, although for wealth the sign of estimate already incorrect, negative, although it's supposed to be positive. So it's not what we expect to see. It is negative, although it's supposed to be positive, and in terms of p-value, it also not significant. So both insignificant, greater than 0.05. So again, there is another sign of one of the sign of the serious problem of collinearity between and the variables. And then if you compare to the F test statistic, this one, F test statistic as well as p-value for the F test. So p-value for the F test 0, meaning it is less than 0.05, so we reject. Remember, for this F test we use to perform the joint overall significance, for the overall significance of the slope parameters. So beta 1 equal to beta 2 equal to 0 for this case, or both slope beta 1 and beta 2 equal to 0, alternative at least one of them not equal to 0. So this one, based on this result, we reject and we conclude at least one of them not equal to 0. But when you compare to this one, it is inconsistent, right? Because this one both insignificant, both not significant, but this one says F test says at least one should be significant, but this one both not significant. So you have contradictory conclusion between F test statistic and the individual health testing using t-test. Okay, and then R square, also R square high, but again, both the two variables not significant. So again, overall this test, the overall significant test shows that the model is significant based on F test. However, none of the slope coefficient is statistically significant based on the t-test. Another way to check the presence of serious problems of continuity is by looking at the VIF. Okay, so if used, you can easily produce VIF by going to view, coefficient diagnostic, select variance inflation factors. After you estimate the model, you go to view, coefficient diagnostic, variance inflation factor. Okay, so you get one. So how these two values are obtained? For the case of whenever we only have two x, when we only have two x in the model, then we have the same values. If we have more than two, then we have different values. So this one, As explained, let's note how this value is obtained. It's obtained by regressing each of x on other x. And then we get r square, and then you calculate 1 divided by 1 minus r square. So for example, this one, so let's say, how we get this one? 482 is obtained by regressing income on wealth. Or wealth on income, we get the same r square. Whether you regress income on wealth or you regress wealth again income, you get the same r square. That's why we get the same VIF. If let's say you have 3 variables, and then you will get different values of the VIF for each of variable. So this one, if you regress, for example, you regress income INC against wealth. Okay, just name to save the earlier one. So you see this one, when you regress incomes against wealth, the r square is 1, and then you calculate the given formula. This one, 1 over 1 minus r square, and then you get, so here we get 500 basically, the exact value, the one, this one because we what we call that, we round out the value of r square, so we get about 500. So basically, if you get 482 just now. So basically, that's how we get the VIF. So if you regress one independent variable against other variables, if they say you have 3x, then you regress this variable against the other 2x. Okay, not only one, but the other rest of the x in the model. You regress each of x against the rest of x in the model. If they are 3x, then you regress one of x against the other 2x. Okay, and then c plus c, then x2 space x3. And you get r square, and you calculate the formula 1 over 1 minus r square, and you should be able to get this one. Okay, we have method. So this value clearly greater than 10, so that indicates that there is very high collinearity between the two independent variables x1 and x2, income and wealth. So there exists serious multi-collinearity problem. Alright, so there are two important points should be emphasized here, or you should remember, or you should understand. First, multi-collinearity does not cause the regression coefficient to be biased. Their probability distribution are still centered over the true values if the regression specification is correct, but they have unsatisfactorily large variance. Okay, so the sampling, the present of multi-collinearity will make the sampling distribution for the experiment to be larger. So let's say we are estimating here. So we can take, this is the true value, but normally we don't know. So we just take sample, and then we get estimate, and then we estimate put hat, beta 0 hat, beta 1 hat, beta 2 hat. So the true value, bias, remember I explained to you what is the meaning of bias estimator? Unbiased estimator. Unbiased estimator when the average, so this is the, when you estimate from a sample, let's say different sample will give you different estimate of beta hat, beta 1 hat. This is what we call sampling distribution for the estimator. So we use the ordinary square to estimate the true value beta 1. This is the true value beta 1, but we do not know lah. This is for population, just like mu and x bar, they're the same concept. Mu we do not know, so but we take a sample, we calculate the average, that is our sample mean x bar. So it's the same concept lah. So this is the true ratio between y and x in the population, y and x1, x2 in the population, the entire population. But we do not have access to all elements in the population, so we just take a sample and then we estimate. And then the estimate we can have different values. Can be here, can be here. Okay. So unbiased estimator means that the average of all possible estimate equal to the true value, then it is unbiased estimator. Okay. So the present of, if let's say this is the case of if there is no multi-causality, but then we have a situation we estimate, but there is multi-causality. The present of multi-causality will make the variance of distribution to be larger. Okay, so we have larger with the present of multi-causality problem. Let's say our x and x1 and x2 has high correlation between them, then we'll make the distribution to be larger, sample distribution to be larger. So this is it. Although it is still unbiased, but it has larger variance lah. Okay. So it has larger variance. So it is still unbiased, meaning that the average of all possible estimates still equal to the true value of parameter, but what the present of multi-causality will make the distribution sample to be larger. So meaning that there are more possible, wider possibility of estimate beta, where we take a sample previously just between this from here to here, the possible value of estimate. But now when you take a sample, it's possible you get here very far from the true value, or you get here, okay, very far from the true value. Yeah, so that's the problem of having the effects of or implication of having multi-causality problem. Second, the standard errors and t-test remain valid, although it is still valid, but it is less reliable lah. So because we have however, the standard errors are larger than they would have been in the absence of multi-causality, warning us that regression estimates are erratic. So because it makes the standard error to have to be larger, I mentioned before. So we have a tendency to we are more likely to not reject the null hypothesis. Okay. If you recall back what we discussed earlier, where it is here. Alright, this one. Recall that how we calculate the test state using the formula that I explained before. This one, the T, we calculate this one. So when the present of multi-causality will make the standard error to be larger, so that the t state is going to be smaller. So this is larger, so the whole t smaller, because we divide by larger values. When t becomes smaller, then we are more likely, because t moving here to the center, smaller t, so we are more likely to conclude that there is no significant. So we are more likely to do not reject the null hypothesis and conclude that the true value equal to 0, while the fact that it's not equal to 0. Okay. So it make it increase the chance for us to make incorrect conclusion. Okay, so we say that there is no significant effects of X on Y, but in reality there is a significant effect. But because of the presence of multipolarity, now we make incorrect conclusion. Okay. So how to overcome the problem? What is the option that we have to remedy the problem? So the first option, just ignore the problem if the problem is not that serious. Okay, remember the implication of having serious multipolarity, it makes our estimate to be incorrect, the standard error to be larger, so that our t statistic smaller and p value insignificant. P value insignificant. So you have to check. There are number of things you have to check after you estimate. You have to check whether it is significant or not, and then you have to check the sign of estimate whether it is consistent to the sign what we expect. If we expect positive, but we get negative, and then you need to do something lah. You cannot ignore the problem. Okay. So your equation will have good estimating power and suffer no problems other than artificially high standard error if the only problem is multipolarity. Coefficient estimate will be unbiased. If you drop a variable, you may run into the problem associated with omitted variables. So if the problem is not that serious, and then you believe both x1 and x2, let's say that one, are important to explain the dependent variable y, and then you can just ignore the problem as long as they are still significant, they are still having the same sign of estimate. Okay, because if both are important variable explain y, if you drop any of them from the model, it's possible that your estimate is no longer unbiased, but it is biased estimate, meaning that you have, when you drop any of the variable, then you have meaning that the average of your estimate is no longer equal to the true value. So it's no longer equal when you drop. So you have to make a careful decision. Okay, whether you really need to drop or not the variable. So only in the case of there is serious problem, then you drop it. Not you do not drop the important variable. And then some econometricians argue that if the model is otherwise okay, then just ignore it. Multipolarity increases the standard error of the estimation, hence making the t statistic become smaller. If the t statistic is big enough for us to reject, so coefficient to be statistically significant to reject the analysis, and the sign of the coefficient is still correct as what we expect, and then it shows that the issue of multipolarity is not that too serious, and then in this case we can just ignore the issue, although your BIF greater than 10. Okay, even though you check BIF greater than 10. Your barring inflation factor. However, if the problem is so serious, just like the example that we had just now, and then you have to remove one of them, drop one or more of the coordinate variables. Another way is to drop one of the independent variable, which is the source of problem. Let's say S1 and S2 are strongly correlated, just like what we had, the example that we had just now. Hence, we can only choose either S1 or S2 to be included or to retain in the model. Using theory, so which one we should retain? So you have to make again a decision. You should retain or to keep the more important variable to explain why, and drop the least important. Do not drop a variable strongly supported by theory. If you do this, you run the risk of having an omitted variable bias. So to review, omitted variables may make the estimate coefficient bias and standard error too small, and this problem is worse than having coordinate. Just mentioned just now. So if you drop an important, very strong, very important variable to explain a dependent variable, then it's possible that the estimate that we have, or we produce estimate, the one that we call as a bias estimate. So the average of all possible estimate will not equal to the true value of the parameter. So for the given example, just now we have to draw. So we have large that indicates for the CS problem, and then when we inspect the result by estimate, when we inspect the result by estimate, then we have one of them to have incorrect sign, p value significant, then insignificant, and then contradict to this one, f and contradictory result of the f overall significant test and the individual significant test. So we need to drop one of them. So in this case, which one is more important? So you have to decide. So if we believe that income is more important to explain the consumption, then we drop the wealth variables. Okay. So if you drop one of them, so let's say we re-estimate the model without one of them. So tweak the equation, and you can compare later on. So you have again consumption and income without wealth. Okay, just name equation 2. So you compare, this is the original one. Okay, this is, so this is the one after we exclude one of them. Well, so you see now, so this option. So this one's a sign, okay. Now this one significant. So unlike before, for the income, p value not significant, insignificant. But now after we exclude wealth, we have significant. So now we can conclude that there is significant influence of income on consumption. Okay. So this one, okay, I mean there's no BIF because only one variable left. Later we have another example. We have more than two variables in the model. If you estimate, if let's say you decide to remove income and then you just retain wealth. And then you see now it has a positive sign of estimate instead of negative, previously negative. Okay, and then it is significant as well. Okay, so you see the danger of having serious multi-coding problem. It leads us to the incorrect conclusion. It's supposed to be significant, but because of multi-codality, then it makes the estimate to be insignificant, not significant. Okay. The third possible way is to transform or redefine the variable. Sometimes the existence of multi-codality could be the result of misspecification of the model. So for the given example here, so let's say we want to model the number of cars sold annually, and then we use annual income, the annual household income, and then price. So it's times data, so average annual price of new cars. And because of the inflation, so income and price will strongly correlate over time because of both of them increases as a result of inflation. So because of this, it just like that the two variables are having strong correlation between them, because they are both of them increasing the values. In terms of the value, they are increasing because of the inflation. Okay. So hence we need to redesign the model to take into account of the effects of inflation in order to solve the problems of multicollinearity. The way is by substituting the income and price with the inflation adjusted income and price variable. So that explained in the additional notes. How to adjust time series data for inflation. This one. So let's say you have time series data, and then you can adjust, you can remove the inflation, the what we call that, you can adjust for inflation, the effects of inflation by using consumer price index, CPI. So time series data that measure in currency value such as income, GDP, tax revenue, and price are increasing over time due to inflation. This phenomena will produce inaccurate inflation results. For example, let's say you want to construct a model using oil prices as a dependent variable and wood prices as independent variable, and we will find that this is positive and significant relationship between the two variables. This, however, happened due to inflation, not because of the actual relationship between the two variables. Okay, they are keep increasing because of inflation, and then so meaning that they are basically there is no actual relationship at all between the two variables. But when we regress, we get positive, we get positively related. For example, because of inflation. So you have to remove the influence of inflation first. So we need to remove the influence of inflation by adjusting the variables to get the real value. So for this purpose, use CPI, consumer price index, which measure value for certain goods from time to time. You can convert nominal value to the real value by using the formula. So nominal value divided by the price index, and then divided by 100. Okay. So the example given here, so I say that the real or nominal, not the real, the nominal. So this normally we call as a current price. Current price, data at current price. You refer to a data service. They want the data at current price. They want the nominal price. So if you have the CPI and then you calculate like this, so you can see the real income after you remove the effects of inflation. So you see the difference lah. So although after 10 years, in terms of the actual amount is increased, but in terms of the real value, just like the power purchasing power, it is actually decreased. Okay. So if you have the data like that, and then try to remove the influence of inflation first before you estimate a model, in order to reduce the chance of having a multi-quality problem. And then the last one, increase sample size. The next factor to look at is the sample size, the number of observations. So if you are working with cross-section data, and you are undertaking a survey, you could increase the size of the sample by negotiating a bigger budget. If you are working with time series data, you may be able to increase the sample by working with shorter time interval for data. For example, using quarterly or monthly data instead of annual, so that you have larger sample size. Increasing the data will provide more information on the described procedure. So meaning that it reduces the chance of having what we call that coincident linear dependence between variables. So let's say you have x1 and x2. Just now we have our variable x1, a list of x. If you have small data, you have small sample size, so there is a high possibility to have coincident relationship or linear relationship between variables. Let's say you only have 3, for example, let's say you have 3 variables, 3 observation, and then it's possible that for that 3 observation you have a coincident linear dependent. For example, this one x1 equal to 2 times of almost equal to the value of x2 plus x3, for example. So that is possible when we have smaller sample size. The chance of having that linear dependence higher, or we call as coincident linear dependence. So when, in order to reduce the chance of having that problem, then what we can do is increase the sample size. When we increase sample size, then we reduce the chance of having linear dependence between independent variables. Okay, because now when we include more observation, then we have more variation in data. We have more variation, so let's reduce the chance of having coincident relationship between independent variables. So that one of possible way lah. So try to increase sample size if you have a problem. So if let's say you want to keep the variable, you believe that both are important, x1 and x2. So you want to keep both, but you have problems of linearity. So one way that you can do is try to increase sample size, okay, to reduce. If let's say the linearity happens because of the coincident what we call it, having similar values or linear related values between variables. Okay, so half an hour break. So we continue 7:53. Around that, 50 or 55, around that. Just before 8. We do